Hi, everybody. Um, what I'd like to show you right now is I'd like to solve this little problem that everyone asked about for mastering physics. And I'd like to go over the activities. And the activity today, activity 4. And then show you some things that I found to be I hope to be very helpful. Okay, so what we're looking at with this quiz number, Mastering Physics Quiz 3, question number 1, is we have this surface. I said we have this surface. There we go. And we have a mass on it. And we're pulling it with a string with some tension. And we want to pull it such that it just doesn't move, right? That we haven't broke the static friction. Oh, so we better write in the static friction. Let me change colors here because static friction is it's going to, yeah, there we go. And we want to look at the other forces on it. Okay, so we know there's a force of gravity pulling on it. And there's also someone pushing down on it with their finger. Let's call that force push, or force P for Pete, pushing down on it. Okay? And so, if we want to ask the situation, we always want to ask, what's going on with the acceleration? Because that's how, this is all going to work. Because we know maybe the very first thing we could write is the vector sum of the forces equal mass times acceleration. So what direction is the acceleration in? We say, oh yeah, we want it to be static. So we recognize in this situation, this has to be 0, right? And because this is so rectilinear here, x and y, I'm going to do this separately. I'm going to say the vector sum of the forces in the x direction equals 0. And the sum of the forces in the y direction equals 0. And a good thing to do now is to define directions. This is the positive x direction, and I'm going to call this the positive y direction. Okay? Is x and y. And so let's take a look at the vectors, at the sum of the forces in the x direction. What are they? We have tension pulling forward, right? And then we have the force of static friction pulling backwards. So these must be equal and opposite because they're pulling in opposite directions. And we remember the force of static friction is just mu s times n. So we're all set there. That's my x component of forces. Now how about in the y direction? So we got these two forces pushing down. Oh wow, they should be accelerating downward. And what we realized, we left out, we got this surface here preventing us from accelerating downward. So yeah, right, we got a nice normal force. Shame on me, I left out that normal force. Are there any other forces I'm leaving out on this guy? M naught. Force of gravity equals M naught times G. Okay, so let's do this. We've defined y, the positive y direction is up. So we've got a normal force minus the force of Pete pushing down minus the force of gravity, right? And all those forces, when you add them together, better get 0. So we're all set now because the way they're connected is the normal force. And then we go back and we say, well, what are we looking for anyway? And it says, what is the minimum downward force on the box necessary? Right. So we want to find this guy. How hard does Pete have to push down on the box in order for it not to move? Well, let's do it. The force of Pete is going to equal then the normal force minus the force of gravity. Yeah, that makes sense, right? Because the normal force has to equal these two together, right? So the normal force minus gravity is what's left over, that downward pushing force, right? And so we can just set this up then. The force pushing down has to equal the normal force, which is the tension, minus mu s right, minus the force of gravity. Okay, because this is, well, that's it. Okay. So let's take a look at the next problem.